Hello everyone and welcome back. So in the last video we learned what a sequence is and we learned a general representation for a sequence, and then also we plot some terms of the sequence as well, right? Now I know you want to learn about convergence and divergence of a sequence, but before we get there, let's talk a little bit more about this general representation. So what did I tell you? Well, I told you that if you have a sequence that's represented in this way, like if it has explicitly written few terms of the sequence, we can actually represent that from a simple expression, right? Now in this video, my goal is to teach you how to get that exact expression. Okay, now, but I should warn you that there's no clear one method to do that. It's a trial and error method, but I will give you some guidelines, some tips. Okay, now my first advice is that make a table. All right, make a table with two columns. In your second column, put all the terms of the sequence that are given to you. So here it's -1, 1/2, -1/4, and 1/8. And in the first column have simple n. Now simple n means the position of the sequence, right? So this is the first position, this is the second position, this is the third position, this is the fourth position. Likewise, have the relevant position. Okay. Now try to make a connection between n and each relevant term. Now look at the overall behavior of the sequence. I mean type of the numbers you have. Here you have fractions. So since I have fraction, what I'm going to do is I'm going to think numerators and denominators separately. Now let's focus on the numerator. So in the first term, well, it's not a fraction, but you can think numerator to be -1. Okay. So here -1 in the second term. Okay, in the second position the numerator is 1, in the third position numerator is -1, in the fourth position it's again +1. Now if you compare the position and the numerator, you can say the numerator switch between -1 and 1. Now do you see a pattern with the position? See, when you have negative and positive switch, always look at the even and odd positions. Now you can see that's a hint. Okay, now you can see all the odd positions are negative and all the even positions are +1, right? Do you see that? So I can say, okay, the numerator is -1 to the, let's say, n. Okay, because n represents the position. Okay, so when n is even, it's -1 to the even power is 1, so these positions will become positive. Now when n is odd, -1 to the odd number, odd power is negative, so these odd positions will come negative. Okay, so we got the numerator. Okay, now let's focus on the denominator. So let's write the terms of the denominator right here. Okay, so here the denominator is 1, here the denominator is 2, here the denominator is 4, here the denominator is 8 of that term. Okay, right. Now let's try to make a connection between the denominator and the position. Now do you see a clear pattern? Okay, now think about several patterns. Is it the position plus a 1 number because it's 3 and 4 here? No, it's 4 plus 1, then this should have been 5, right? No, clearly not that. It's not clear, right? Is it twice as the position because 4 times 2 is 8? Then this should have been 6, right? No, that's not the case either. But notice something. Try to write, here's another hint. Maybe you can write your terms, numbers, as powers of some kind of a number. Now here 4, I can write it as a power of 2, 2 to the power 2. 8, I can write it as 2 to the power 3. Right? Now you can see, you can think 2 as 2 to the power 1, and you can think 1 as 2 to the power what? 0. Right? Okay. So can we come up with a pattern here? Right. Can we come up with a pattern here? See, now look at the power and the position. Here you have 0 and here you have 1. Here you have 1 and the position is 2. Here you have 2 and the position is 3. Here you have 3 and the position is 4. So position is always 1 less than the power, or the power is always 1 less than the position, right? Oh, maybe that's the correct way. Power is always 1 less than the position. So power of the sequence is always 1 less than the position. Great. So that's the denominator. Now what you need to do at this moment is now you have to verify. Now let's write the full representation in a one color. -1 to the n over 2 to the n minus 1 power. So you think that it is the representation. Now give it a try. Plug numbers. Plug n is equal to 3 and see whether you get -1/4. So likewise, check your work. Okay, so that's the next thing you should do now. But I'm confident this is the general representation and the n values are going from 1 to infinity. Okay, all right. Now that's how you find the general representation of a sequence out of the given terms. Okay, now here's something that I didn't teach in the previous video. Some people can label n values starting from 0 instead of starting from 1. Some textbooks, some instructors do that, and that's fine. That's also legal. Okay, so you want to be careful. So if you label your sequence to be starting from 0, now you have to make a different table. Okay, so nt, so the values are same, -1/2, -1/4, 1/8. It's just now we are starting your position at 0, 1, 2, 3. Now you have to make the same connection again. Okay, if that's the case, if they want it to be labeled from 0. Okay, now again the numerator is going to be a some power of -1, but at this moment, in this case, all the odd powers are positive but the even powers are negative. So I'm going to say here it's -1 to the n plus 1. Okay, because when n is equal to 0, -1 to the 1 is negative. See, when n is equal to 1, 1 plus 1 is 2, -1 square is positive, so this is positive. So likewise, it match with the pattern. Now the denominator, I'm going to say it's going to be 2 to the power what? Let's see, here the denominator 2 to the power 1, 2 to the power 0, 2 to the power 2, 2 to the power 3. So make a connection between these two numbers. It's the same number, right? Power is same as this new labeling position. So it's going to be 2 to the n. So if you start n from 0 and goes to infinity, then the representation is -1 to the n plus 1 over 2 to the n. So the representation is little bit different, but it tells you the same story. Okay, same sequence, it's just labeled in different ways. But just I want you to know, some people start labeling from 0, some people start labeling from 1. Okay, so read your instructions carefully if there's a question like this. Okay, right, now it took 7 minutes apparently. Let's do another couple of examples of generating this general expression. Okay, here's my next example. Now we want to write the general term of this sequence. Now here's what I suggest you. Pause this video and give it a try. Try to do at least couple of steps. That's how you can really learn from a video. That's how you can learn math from a video. Try to do this simultaneously with me. Give it a try, pause the video, give it a try and check with my answer. Okay, if you cannot write the general term, then try to watch this video and try to learn. Okay, but first of all, give it a try. Okay, so what's the first thing that you do? Well, you have to make a table. On the right hand side, on the right hand column, I'm going to put the terms of the sequence. -1/3, 2/9, -1/9, 4/81. These are the terms of the sequence. Now let's have the positions on the left column. 1, 2, 3 and 4. Now let's try to see a connection. The first connection that I'm trying to get is that there are negative and positive switch between the terms. Okay, pause the video and try to write the general term so that it represents just the part of the negative and positive switch. Give it a try. Now I can see all the odd terms are negative. So guess what? So it's going to be -1 to the n is the general representation for that negative positive switch, right? Okay. Nice. Now let's look at numerator. So you also look at the numerator. Let's try to write the numerator. Let's try to represent numerator generally. Now if you look at the numbers, it's 1 here, it's 2 here, it's again 1. Now I'm ignoring the sign, okay, because we already worked out that. Now I have 4 on the 4th term. Now do you see a pattern? Now you almost see a pattern, right? Pause the video and think. You would have a nice pattern if I had 3 here, right? So then it's 1, 2, 3 and 4. Now on the other hand, look at the denominator. 3, 9, 9, 81. Do you see a pattern? there would be a pattern. So here it's 3 square, and here again 3 square, but this is 3 to the power 4. So actually 3 to the power 3, if we had 3 to the power 3 term, then the denominator would also have a nice pattern, right? All the denominators would have a nice pattern. So there's a problem with the third term overall. Do you agree? This third term seems to be like out of the pattern. Now pause the video and again think, what can we do about this? Now here's what might have happened. Think, we don't know. This might have happened. The thing that might have happened is that there might have been a common factor in the numerator and the denominator, so that the person who wrote this sequence, well actually me, simplified this fraction, okay, cancel out certain numbers and wrote -1/9. It could have been more than 1/9. So how do we figure this out? Well, think about this. All what you would have liked for the third term in the numerator is 3, right? So let's say that you have 3 there. So if numerator was 3, then it's -3 actually. Then what is denominator? It should have been 9 times 3, which is 27, right? Because now 3 and 27 cancel out and you get -1/9, right? So -3/27 is same as -1/9. Okay, right, now do you see the pattern? Yes, the pattern is that in the numerator you have 1, 2, 3, 4. See, 1, 2, 3, 4, which match with this situation. So the numerator is n, right? Simply n, the position itself. What's the denominator? If you write the denominator in green color, in the first term it's 3 to the 1. In the second term 9 means it's 3 square. Now the denominator in the third term is 27 actually, which is 3 to the 3. Denominator in the fourth term is 81, which is 3 to the 4. So the denominator should be 3 to the power, it matches with the position, right? 3 to the power n. So the general term that represents this sequence is actually -1 to the n times n divided by 3 to the n, okay, where n goes from 1 to 4. Now that's very important. The takeaway here is that how we deal with the term that was going off, this term that was going off the pattern, okay? You have to think little bit. It was a term that was simplified furthermore, okay? All right, so let's do another example and stop this video. Okay, here's my third example. Now I have given the sequence, I want to write the general term. I have already given you the table to save time in this video. Okay, here's my first suggestion for you. Pause the video and try to write the general term that represent the negative and positive switch. That should be easy now. So you can see every odd term is negative, so it's definitely -1 to the n. Okay, so let's get that away. Now here's my next suggestion. Pause the video and try to write the denominator this time. Let's try to represent the denominator. Now why would I do that? Because it seems to be like I can right away see to my eye that there's going to be a pattern in the denominator, because it's 3, 9, 27, 81, all are powers of 3. So try to guess that pattern. Give it a try. Pause the video and give it a try. Now what you see? So here denominator is 3 to the 1, here 3 square, 3 to the 3, 27, 3 to the 4, that's the denominator, 81. And now if you compare with the position, now I mean it has to be 3 to the some power of n. But what is it? Now here you have 1, here you have 2, here you have 2, here you have 3. So the position is 1 greater than the power. Okay, or the power is 1 less than the position. So let's say that in that way. Now if you think about the first term, in the first term there's no denominator, or you can think it's 1, right? Really it's 1, so that means 3 to the power 0. So the power is 1 less than the position, so it's n minus 1, right? 3 to the n minus 1. Okay, I hope it makes sense. All right, now here's my challenge. Think about the numerator now while I erase this stuff. Okay, think about the numerator. This is something that you have to do. Okay, pause the video and give it a try. This is a good exercise. Now if you think about the numerator, well, in the first term it's just 5, 10, 20, 40, 80. Okay, what's the pattern there? Now you can see that the very first term is 5. So it has to do something with 5, right? It's kind of, we can kind of sense that the pattern has to do something with 5. So let's try to write 10 as something of 5. So 10 is 5 times 2. Okay, so I'm gonna write 5 times 2. 20 is 5 times what? 4. 40 is what? 5 times 8. 80 is what? 5 times what? 16. Now do you see a pattern? And 5 is actually what? 5 times 1. Now what's the pattern here? Now if you look at the pattern of 5, it's just 5 appears in every term. Every term in the numerator is a multiple of 5. And all the other terms, it's 1, 2, 4, 8, 16. Do you see a pattern in 1, 2, 4, 8, 16? Yes, 2 is 2 to the power 1. 4 is 2 to the power 2. 8 is 2 to the power 3. 16 is 2 to the power 4. Interesting, right? So what's going on here? Every term, in numerator of the every term is just 5 times 2 to the power some power of n. Do you agree? What's the power of n? When you have 1 and the position is 2. You have 2 as the power, position is 3. You have the 3 as the power and position is 4. So it's actually 2 to the power n minus 1. 1 less than the position. That's the power, right? So you have 2 to the power in every numerator multiplied by 5. So in every numerator you have 5. So 5 has nothing to do with n, right? Because it doesn't change with the position. It's just always 5. It's not 5 square or 5 cube or anything. It's 5 is 5. So 5 is in the every numerator. So 5 is independent of n. So let's try to write this general representation in a nice way. So it's 5 times negative 1 to the n, 2 to the power n minus 1 over 3 to the power n minus 1. Let's write them together. Let's write them as 2 over 3 to the n minus 1. Now this is a one way that you can write the general representation of this sequence. Okay. All right. Now if you want to make sure that this is right, go ahead and plug numbers for n and see whether you get these same terms. Okay, if you're not getting those same terms, then you have done something wrong. That's something that you should do at the end of every problem. Okay, and there are multiple ways that you can write this same general representation. You can manipulate this little bit to simplify. Okay. But this is it. That's how you write a general term from a given sequence when several terms of the sequence are given to you. Okay. All right. Great. Now in the next video, we are going to start to talk about the big topic of this lesson of sequences, which is convergence and a divergence of a convergence and divergence sequences. All right. So hopefully I'll catch you there. Bye bye.